Now we're going to see why Ampere's law holds. We have here a circular conductor, and we have, let's say we wanted to calculate the magnetic field here, and we will attach a surface. Let me do it not circular, like the way surface, whatever it is, something like that. We have the magnetic field of a wire is like this, or well, like this, depending if the current goes this way or the way, but it's like this. So in this, for example, we take this little piece because we will take the closed loop integral of the magnetic field dot dl. To do this, we need to take the dl of here and take the integral, but let's do it with this angle theta. So here we have at this point the dl goes in this direction like this, and the magnetic field goes in this direction, could be something like this. They are not perpendicular. I hope you can see that they are not perpendicular. So here we have, let's say that angle is phi. So here we have b dot dl, the closed loop integral of this is the closed loop integral of the magnitude of the magnetic field times the magnitude of the L cosine of phi. This dl cosine phi is the projection of the L onto the magnetic field. So what is like the component of the L, that the component in the magnetic field. So that is, if you down this vector and you take the projection, you actually are talking about this. So this is cosine of phi times the L, and this is exactly the same as let me take a smaller angle theta, like this. Sorry, yeah, because the L needs to be here. So this pink arrow is exactly the component for this angle, the theta. So sorry, the component, not the component, if you have a cycle, remember here is cycle, you have r and you have this theta, this that if you do it infinitesimal you will say it like a straight line, that is this that is the arc length is r times theta, or the theta. So this is exactly the same as cosine of phi times the L. So this is r the theta. So you will take now the closed loop integral of the magnetic field dot the L. This is equal to the closed loop integral of magnetic field r dt. The b, you can take it out, b times the closed loop means all these loops. So all this, if you do it like this, actually it would be to 0 to 2 pi, because remember that it doesn't matter what attached surface we pick, we can take also this surface. So go from 0 to 2 pi, and actually we're taking this from 0 to 2 pi. We're taking all this integral, and we are not talking about the radius. So from 0 to 2 pi of here r dt. Now remember that for a circular conductor, in the previous video we saw that the magnetic field is the magnetic permeability times the current divided by 2 pr. So here we have closed loop integral of b dot dl is equal to mu naught I over 2 pi r times r, and this would be just times 2 pi. So at the end we have that the closed loop integral of P dot dn is equal to the magnetic permeability times the current. The current means the current that is enclosed by the surface, or I prefer the term that is penetrating the surface. And this is Ampere's law. Actually, this is not quite Ampere's law. Well, it is Ampere's law as Ampere defined it, but Maxwell did a correction that is also includes the magnetic field that is produced by a changing in electric field, and we will see this later on some videos.